So, big question I want to talk about first. So, I know we have a data set of the week every week, and we will have a new data set of the week this week, and I will introduce it in 15 minutes. There's just this last thing I want to do, and I'm going to stick with last week's movie review data set for that, and then we'll introduce the data set of the week. So, what is up with this test set? That's what I want to talk about right now. Like, why we do cross-validation, that's unseen data, it splits into train and validation. Why do we keep separately having this test set? And I keep asking you to look at the test set. And this is something that I've thought a lot about. So the problem is called optimization bias, also known as overfitting on a validation set. And what I'm going to show you in a minute is that sometimes your cross-validation score is too optimistic, and the test set is a very useful reality check. I've thought for several years about how to teach this, and it's hard to teach because the problems hit you really hard when your data set is small. But if you take a really small data set, then the test set is also going to be really small, and so you can't really accurately get a test error either. So what I'm going to do this time, and I hope it works, I'm going to take this big data set, this big movie review data set, and I'm just going to make almost all the data as test data, which you would never actually do, but just for teaching purposes. And that way we can simulate a very small training data set of 500 examples. But we have a giant test set. So when we compute the test error, we can actually trust the test error and have that luxury. So from a teaching perspective, we're not worried about the test error being wrong due to low amounts of data. But the training set, this is not an unrealistic scenario that you have a small amount of training data. Okay, so all of the next few lines are basically just from last week. So I'm splitting it up into X and Y. I'm doing count vectorizer with default, or I'm going to do a grid search. And what I'm doing here is I'm just doing a really big grid search so I'm picking this hyperparameter max df. If it's like 0.7, then if a word appears in more than 70% of documents, it is excluded because it's considered too common, like maybe the or whatever. So max document frequency. And I'm just doing a very fine range. I'm trying 0.01, 0.03, 0.05, 0.07. And the reason I'm doing this is so that grid search CV is going to be grid searching through a lot of values. And so when I run the grid search, it's doing 1,000 fits because we have 5-fold cross-validation, and I'm trying 200 different values in my grid. I have 4 things here and 50 things here. And so I have 200 possibilities in total. And so I'm really doing a big grid search. I mean, relatively big. And it's not going to be that slow because the data set is so small. It'll only take maybe a minute for this to run. But we're hitting the validation data over and over and over again. And something kind of suspicious is going to happen. We're going to have to wait for it to finish. But I'm trying this very fine grid of many, many values. And so remember, the validation data is supposed to be unseen data. And it's unseen in the sense that inside of cross-validation, you're always splitting, training on some and testing on the other. But on the other hand, you are using that validation data so many times because you're just doing this over and over and over and over again that you are kind of involving the validation data in your grid search CV procedure. And so I'm going to print the results. And you can see the results. So the best thing is 84% cross-validation accuracy. Again, this is just what it's called inside scikit-learn mean test score. That's the cross-validation accuracy. It's getting 100% training accuracy, so it's definitely overfitting. And these are the parameters it likes. Max df equals 0.25, meaning if a word appears in more than 25% of documents, we're just throwing it away. C for logistic regression is 1. And I don't really believe any of this. And the reason I don't believe any of this is because I only have 500 examples in the training set, as we saw. So my whole split is 400 train, 100 cross-validation, 100 validation. 100 validation, it's just not enough. Like, it's not enough to actually know what's going on to this many decimal places. There's so much randomness. And so here's how I want you to think about it. You could always get lucky and have a particular set of hyperparameters leading you to a particular count vectorizer and a particular logistic regression that just happen to work well for that particular validation set. And actually it's cross-validation, so those particular 5 validation sets, but there's always some randomness in here. And when the data is small, like if I ask you to look at the subscores, I'm guessing the subscores are probably pretty different because the data set's so small. We don't really have a good averaging out of things. And so basically I would say any of these scores has just a bunch of like unpredictable noise to it. And so if I actually try 1,000 times, that's what I'm doing, right? I'm trying this data frame, sorry, it's 5-fold cross-validation. So 200 times. This data frame has 200 different hyperparameter configurations that I looked at. You know what? Some are going to get lucky. And the ones that get lucky are going to float to the top. And so if there's a bunch of randomness in each of these, and then I just say which is the best one, you know what? The best one was probably had good randomness. And I don't really trust this 84.4%. So do I really believe that these are the best hyperparameters? And do I really believe that it can achieve this accuracy? No, because I just threw a dart at a wall 200 times, and you know what? I'm going to hit the bullseye one time. And do I believe that these hyperparameters, the best ones, are better than the worst ones? Absolutely. I mean, this looks horrible, 50% accuracy. So sure, I believe the best hyperparameters are better than the worst ones, but I don't believe it to 3 decimal places and splitting hairs that this 844 versus 842 is meaningful. So no, I've tried it too many times. The data set is small. And so what I want to show you is that we said we had 84% accuracy. Let me run it on the test set. And remember, the test set is huge here, so we're not too worried about randomness. The test error we can kind of trust because we've made this contrived kind of fake scenario where we have a huge test set. And what we see here is a very significantly lower score, 78.5%. You have to go way down this list to get to 78.5%. So this is way, way, way optimistic, this 84%. And that is why I like you to have a test set. Of course, in reality, your test set might also be small, and so there's going to be some randomness in your test score as well, and that's going to be another issue for you to worry about. But it is kind of a sanity check. So here, if you went to your boss and said, hey, I got 84% accuracy, therefore I expect this to get 84% accuracy in deployment, you are wrong. You are misleading that person. And we have to be very careful about this. The test set gives us a sanity check, and here says, whoa, 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 hold on a minute. You just tried 200 things. There's some randomness in here. And you know what? The best one of those 200 things, well, it just happened to do really well, but that's not meaningful. If I try that on a different unseen data set, here's like, let me bring you back to Earth here. You're getting 78% accuracy. And so this phenomenon is called optimization bias, in the sense that you're optimizing, searching, and getting biased results. It's also called overfitting on the validation set, and you're just hitting that little validation set for way more than it's worth. And so, yeah, this is why we have the test set. Here we can trust the test score because I have this made up example of a big test set. So yeah, I mean, this is very hard, is what I'm trying to say. This is very hard. This is very nuanced. What do I do with this information? Well, the first thing you can do is you can at least not mislead your stakeholders, your collaborators, and tell them something that's way too optimistic. Even if you do nothing else, even if you say, you know what, I'm going to stick with these hyperparameters because I don't have any better ideas right now, but at least I'm not going to oversell them. That's wonderful. That is so much better than telling someone to expect 84% accuracy. If you want to use, you may also want to try something different. And we basically say only use the test set once. And if that's true, well, then you can't really do anything else. But in a more realistic approach, if you want to use the test set like 3 times or something, that's okay. So maybe you get worried, you say, I'm going to try something else. You try it again on the test set. I can forgive using the test set, a few times. Maybe you want to try a simpler model. But you can't use the test set 100 times, otherwise the same phenomenon will happen again. You'll just get something that happened to be good on that test set that you had. So the other thing I want to say is that there was a ranking here, right? It was saying not only is this 84 kind of bogus, but it's saying that 0.25 max DF is better than 0.43 max DF because it's 0.4% better test accuracy. And I'm saying we can't trust that either. We can't trust the sorting. If all these numbers are wrong, the order of the numbers is probably wrong too. So here I'm doing it with 0, like the best hyperparameter. This is sorted, so I'm taking the best hyperparameters, and I should get that same score that we saw before. And now I have a 5 in here. I'm taking the 5th best hyperparameters, meaning these. Oh, actually 5 is the one after that. 0, 1, 2, 3, 4, 5. Oh well. Okay, 5 is the one directly underneath that we can't see. Indexing, getting me. And so what we see here is that this one actually does better on our giant test set. So 78.5, 78.8, not a big difference, but basically I just want to hammer home, if you can't trust any of these numbers, you can't trust the ordering either. And so be careful about this. This is again part of like the overall aims of the course. Like when I made the course, one of the learning objectives for the entire course was teaching you not to overstate your results, because that's just such a big problem in the field. And the more you can be paranoid, the more I'll feel like I did my job with this course, because there's a lot of things to go wrong that we've been seeing. This golden rule stuff with no error message. This thing, if you didn't have a test set, you wouldn't really know. And so we need to be very vigilant here. And just looking at the time, I'm going to skip this. It's not too important. And I want to say that basically the size of your data set is an extremely important variable when you're working on this type of problem. If you have small data, just everything is worse. Everything is worse. Your scores cannot be trusted. You're going to overfit more. And your test error cannot be trusted. So yeah, there's the more data you have, the better the situation is. And maybe you have so much data that you don't even use cross-validation anymore, and you just split into train and validation. And maybe that's okay because you just have so much data. So I really want you to be thinking critically about how much data you have and how much you can trust your scores. And you have some diagnostic tools to think about how much you trust things, like looking at the test score, like looking at the sub-scores from cross-validation. And so I want those to be kind of tools in your toolbox. And I just want to say, last thing, and then I'll go to the Q&A. When you have a lot of data, this thing we just talked about, overfitting on the validation set, is less of a problem, but also just regular overfitting is less of a problem. Because if you had infinite amounts of data, you would probably expect your test score to be equal to your trained score. The regular type of overfitting that we see is also because of lack of data, because it's just like you have this particular small training set and you get over specific to that. But if you had the biggest training set ever, both of these problems would go away. So more data is really very excellent. Now I'm at a Q&A. So first I see a raised hand in Zoom. Let's do that first, and then I'll take a look at Piazza. So
hi.
Yeah.
How much data is enough data for the data set?
Yeah.
I mean,
how much data is enough data?
It's
the age-old question.
Isn't it more like a, because we always say more is good, but we never set the baseline for enough.
Yeah, there is no real answer to
before
this
we start the training.
I cannot tell you how much data you need. I could tell you some theories about it, but I don't think they're useful. I think it's more useful for you to look at the observations, be a detective about it, and ask, are things making sense? And so Sure, if I have 500 data points, I'm going to be, my guard will be up because that's a low data scenario. But I would look at these subscores from cross-validation. I would look at, um, my test error versus my cross-validation error. But there is no, you might have a gut feeling, but that question really depends on the details of the problem. And I think it would be dangerous to try to rely too heavily on rules of thumb rather than actually looking at your results. And looking at the different folds of cross-validation is a really nice thing to do because it's basically saying, if I split things differently, how different would things be? And you don't want them to be that different because the splitting is just arbitrary. And so I really like that strategy. I see one more raised hand,
So
so go ahead.
Okay. Can you can you hear me?
Yep.
All right. My question was about like when you were doing the splitting on the data set. Can you do it like a few times to get like less biased results on your
When you're doing the splitting on the data set, can you do it a few times? So that's exactly what cross-validation is. What cross-validation is literally is saying, instead of just splitting into train and validation, I'm going to try 5 different splits and average them because that's going to give me more accurate results.
but
And
I mean like
so,
but
go
I meant
ahead.
like to get like more 500 out of those test data set. Like you had about 42,000, I guess. Like you can get like another different 500 like by randomly
Well,
shuffling
yeah,
the data set
but
at the
again, like,
very beginning.
the that's, I mean, okay, so realistically, you wouldn't have 50,000 data and only use 500 for train. You might have like 800 and use 500 for train, but you don't want to do the train test split over again. No, because then the test set is not unseen data anymore, and that's dangerous. So I would say do the train test split once, don't mess with that, and then use cross validation. And if you can, use more folds, use 20 folds for cross validation. But I would not redo the train test split because that basically compromises the test set. And when you're doing it again, and now you have test data that used to be training data, it's just not unseen data anymore. And it's not worth it. It's like cheating on your midterm. It's just not worth it.
I see. Just one more quick question. So like when you're talking about the small data set, let's say we got 60 examples with like 14, 20 features. You're saying we shouldn't really apply machine learning on those small data set. Like in lab
Yeah.
experiment, it's super difficult to get the results. Like,
My
I mean,
personal opinion is if you have 60 rows, none of this stuff is probably going to be very useful. But again, I don't want to make these kind of sweeping statements, but the less data you have, and 60 is pretty darn little, I would be very skeptical of any of this stuff applied to that.
even not neural network, right? Like,
Well, that would be even worse. We'll talk about that later,
okay.
though.
Awesome. Great.
Yeah,
Thank you.
okay. One more raised hand. Oh, maybe it's unraised. Okay. Okay, so let me now go to Piazza. Okay, I see 3 questions here. Lecture 6, bias optimization. Can we shuffle the splitting a few times? Okay, so I think that was already asked in voice. So I'll skip that one. Getting confused on the different data splits. I might be forgetting things from a different lecture, but I thought we were using a validation set and test set interchangeably. Right, so we're not. Test set is the thing that we're putting off to the side at the very, very beginning. And then cross-validation is taking the train part and splitting that into train and validation for hyperparameter optimization. And we have one other question here. Isn't the point of validation set then we can use it multiple times? Yeah, so you can use it multiple times, but the more times you use it, the more paranoid you should be, the more on guard you should be. And if you use the validation many times in combination with it being small, you should be even more worried. And yeah, the larger it is, the less worried I would be about this. But I wish I could just give you like a set of rules, but if there is one, I'm not aware of it. So that's why I'm trying to kind of talk to you about the diagnostics again. And like one thing we could have done here was look at the different folds, and I think they would be pretty different. Okay, so in the interest of time, I'm going to keep going. I'll ask you at the end your feedback on the Piazza versus the Zoom. One benefit of the Piazza is for the people who are not here right now, it's archived for them on Piazza as well. But anyways, I'll ask you about that. Okay, next thing. So the data set of the week. So the data set of the week is a famous old data set on predicting if someone is low income or high income based on how they fill out the census. And so you can get the data set from Kaggle. Again, this UCI data set repository is like this old and well-known thing. Not very modern, but very good for what we want to do here. So I'm going to read in the data and just immediately train test split. And that's, again, a habit I would like you to get into. I don't, even this, I mean, I know I'm now being a little extreme, but let me just be extreme and say, even just looking with our eyes at the data, I would rather you do that after the train test split. So you don't even touch the test set in the slightest possible way, not even look at the first 5 rows. Let's just keep it clean. Read CSV and then train test split and then bam. So yeah, the census asks that this last column is the income, and we're going to try to predict this column from all the other columns. So we're going to try to see if we know all these other things about a person, can we predict their income level if we didn't already know their income level? That's the supervised learning task we're gonna be doing here. Just a note that a lot of these old data sets, the Titanic, all these things, they collected the data with male and female sex, which is perhaps an outdated view of the world. So my using these are very popular data sets that have a lot of features that will help us learn. And so that's why I'm using them, but I'm not implying anything about gender here. This is simply the way the data was collected at the time. Okay, let's keep going. So how much data do we have? We have 26,000 people who filled out the census. They answered 15 questions. And what are these questions? Well, we've kind of seen them up here, but this is what we have. So we have their age, something about their working, education level, where their native country, all these other kinds of things. And so the .describe method in pandas is a pretty nice way to just get a sense for the numerical variables. It tells you the range, the min, the max, some quantiles, mean, standard deviation, that kind of thing. So that's kind of a nice thing to look at when you're coming to a new data set. And the target value that we're trying to predict is income. So there's 2 values here, greater than 50K or less than or equal to 50K per year. And we can just start with dummy classifier and we get 76%. And I don't remember if it's, okay, so we have 76% in the lower income category and 24% in the higher income category. So anything we do that gets worse than 76% accuracy is just a disaster, because dummy classifier that predicts low income every single time, and now you've implemented that, gets 76% accuracy. So what I want to show you now is this tool called Pandas Profiling, which you should hopefully have installed because it was part of the environment that we had you install. And it's basic. So first of all, for those of you coming from computer science, profiling has a specific meaning, like to see how long the code takes to run and stuff. That is not this at all. This is a different type of profiling that's like, let's look into a data set and just sort of get some attributes about it. This pandas profiling thing is really slow to run, but I guess it finished now. And it's just this really cool kind of interactive thing about the data set. So number of variables, number of observations, size in memory, and it tells you all these really interesting things about the variables. So here's the histogram of age, go column by column. Here's the histogram of work class, mostly private, da, 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 da. I don't even know what this thing is, I forget, but we could look it up. This is a famous data set. Here's a histogram of education. So this is kind of the variables section that we're in, looking at all the variables. Yeah, so there's even more details if you want. And then there's interactions between variables. We'll talk a little more later about how to kind of interpret this type of stuff. But basically, anyways, not too important right now. Missing values. We'll talk about missing values on Thursday and a bit of the data. Anyways, what am I trying to say here? This pandas profile thing is just a super handy tool. I'm not going to go into more detail than I already did, but it's just a nice way to start exploring the data. And again, make sure you train test split before you do this. It's better if you don't look at the test data in this. But yeah, it's just a great tool to know about even before you start. Just what am I dealing with? And is there anything weird? And there is a few things that are a little bit weird. Like for example, this variable capital gain, based on this histogram, it seems like there's some people with like insanely big capital gain and almost everyone is 0, and that might have implications. And in fact, we're going to talk about that later in the course. So there is actually good stuff here. So just something for you to know about. Now we have another Q&A. So let me go to Piazza and see what we have. I think we don't have any new questions. Any questions about this new data set? Does income only have 2 classes? That's correct. So they binned the income into these 2 categories here. They may have collected more information and then binned it, or maybe this is just the information they collected in the census. I'm not sure. Would it be frowned upon to profile the data before train test split? It would be frowned upon by me, so I guess I would say yes. I'm trying to teach you the strictest habits I can think of, and I hope you'll follow them when you go out into the world. Is it possible that some people profile it before splitting? Sure, but I think it's better not to. It doesn't cost you anything, so we might as well just follow these good habits. Which classifier would be best here? So yeah, we're gonna talk about that. We're gonna be going a lot into this data set for the rest of today and Thursday, and by the end of today, we won't yet be ready to really attack this data set because there's some new challenges compared to the previous weeks. But by Thursday, we will do the full pipeline on this data set with pipeline, hyperparameters, classifiers, and so we'll answer that question on Thursday. Okay, so let's take our 5-minute break now and return at 11:39. So, encoding of categorical variables. This I'm excited about this very mundane topic. I have strong opinions about it. Okay, so let's do our thing. Let's make a classifier, logistic regression, decision tree, whatever you want. We'll introduce more classifiers as the course goes on. So my X is going to be everything except income. My Y is going to be income. And bam, problems. And the problems come from cannot convert string to float. So we have a bunch of text in here, strings, not long text like a movie review, a whole paragraph, but still string type columns. And logistic regression or anything in scikit-learn is expecting numbers. And so it said, hey, whatever you gave me, I'm going to try to turn it into a number. And I can't turn the United States into a number, so I'm going to freak out. And this is just the exact same error message we had a week ago when we tried to do stuff without count vectorizer on the raw movie review. So we need to pre-process the data into numeric values. That's what I'm really trying to say here. But we don't really want to use count vectorizer because it's not like free text and we're trying to look for keywords. These are actually categorical variables, meaning if you look at one of them, say work class, and we actually saw this in the pandas profiler up there, but just to show it again, Like there's only 8 categories here, or 9. So this is not like text, right? We have most people in private, a bunch of people in self-employed, a bunch of people in government, all these kinds of things. So what we want to do is use this information somehow. So first thing I did, which I'm going to do pretty much all the time when we start working on a new data set together, is I'm just going to manually take my human brain and categorize the features into what type are they. And so I have some numeric features, and I have some categorical features. So again, numeric is like, you know, this age or whatever this thing is. And categorical is it one of these categories? And so here's my first kind of straw man approach to dealing with this. Let's just delete the categorical features. That'll solve the problem. Sure. I mean, it will solve the problem. We can just delete all the categorical features. Now we don't have them anymore. And now we can run fit. But this is not a real approach to this problem because we want that information, right? Like knowing someone's education might be useful in predicting their income category, and just throwing that away is silly. So we want to turn it into numeric in some other way. And by the way, later in the course, we'll talk about some ethical issues that you might be able to already see, or you may have seen in the news in the past few years. But some of these things we might not want to be using to predict things, like race, for example. And we'll talk more about that later in the course. Okay, so ordinal encoding. So here's a new thing in scikit-learn. It's called ordinal encoder. And this is a transformer like count vectorizer in that it has a fit and a transform and a fit underscore transform, which just does both at the same time. So I'm going to make one of these ordinal encoders. This d type equals int, that just makes it cleaner for teaching purposes. We don't need that in general. Just make things print out more nicely. And so I can run it on the categorical features. So here I'm subsetting the categorical features. I'm running fit transform. And you can see it turned everything into numbers, which is great because that's what we wanted. We wanted numbers. And I can make it a data frame so it prints out more nicely. So here's what we have. These are the different people, the rows who filled out the census. These are the categories, and it's turned all of these into integers. And how did it turn them all into integers? Well, it just like picked whatever default order they're in Python. I probably sorted alphabetically. And so we can look at the mapping here. So question mark became 0, federal government became 1, local government became 2, etc., etc. So I think 0, 1, 2, 3, 4, private. So 4 here means private because it's number 4 in this list, etc. By the way, this question mark thing, we're going to talk about that next class. So for now, we'll just treat that as a regular category. Okay, so let's smush this back into the original array using pandas concatenate. So I'm basically taking these first 5 columns from before and merging it back into these first 6 columns and merging it back into these encoded text columns. So now we have the numeric columns, we have the categorical columns that we turned into integers with ordinal encoder, and we're good to go, no error. However, there's a problem here. So think about logistic regression. Logistic regression is just nice to think about, but this is true for anything. What does the logistic regression do? It's going to learn a coefficient for every feature. So maybe it's going to learn a positive 5 coefficient for education num, and that's basically going to say higher education means I'm more likely to predict high income. And maybe it's going to pick, I don't know. Okay, I just realized something that I'll deal with later. I just realized they provided education and then they already provided education turned into a number, so we could just get rid of this original one, but I'll deal with that later. Okay, and maybe it's going to learn a coefficient for occupation that's negative, that says the higher occupation you have, the less likely you are to have high income, the more likely you are to have low income. Or maybe a decision tree will learn a threshold. If occupation greater than 7, go down this tree, and if it's less than or equal to 7, go down that tree. But that makes no sense because the occupations are not ordered. They're just a bunch of, yeah, exactly. I'm seeing that in the chat. They're just a bunch of things that happen to be sorted alphabetically, and this order makes no sense. There's no reason why you should think that it's 1 and then 2 and then 3, and as this number tends to be higher, I should think this, and as this number tends to be lower, I should think that, if it's just a bunch of categories. And so ordinal encoder is not the right approach for the vast majority of these columns, because it's imposing order on something that is unordered, and you're just going to overfit. You're going to overfit to that, but it's not going to generalize. It just doesn't make any sense to say the higher your country is when sorted alphabetically, the more your income is. That's just, you're not doing your logistic regression any favors by setting this up that way, and it's going to do worse. And we can look at the test errors of that probably on Thursday. So yeah, here's, for example, the country. So here's the mapping from the country to the integer, and it's just alphabetical and doesn't make any sense. So let me actually, sorry, I just want to grab one of these. Sorry. Let me add a Q&A right here to just say, are there any questions about why this is not a good idea? Because I want that to be clear before we solve the problem. Any questions on why ordinal encoding is not a good idea? I see a raised hand. Go ahead.
Hi, can you hear me?
Yep.
I was gonna ask, what happens when we run the transformer, we do a fit transform, and then presumably on the test data, we do just the transform?
Exactly.
What happens if there's a category that appears in the test data, but not in the training data?
Great question. We'll get to that in a couple minutes.
Okay.
So let me look at Piazza. I see, they're kind of sorted by upvotes rather than by time. I think they have been answered. So I'll leave that for now. I'll look into the Zoom chat. Yeah, okay, great. Yes, all the things you're saying make sense. That's good. Let's keep going. I'm going to lower your hand, by the way. Okay. Moving on. So yes, one-hot encoding is the next thing we're going to talk about, and it's exactly what someone suggested in the chat. Can we split each category into its own feature? That is called one-hot encoding. The reason it's called one-hot is that we are going, well, I'll actually answer that in a second when we're actually looking at it. So let's do it and then talk about it. That's really the way to go here. Okay, we did it. So I made a one-hot encoder instead of an ordinal encoder. I ran fit transform, and here's what it looks like. So remember, work class was just one feature at the beginning. Now work class is occupying a whole bunch of columns. And it was kind of the same thing with count vectorizer. We just had a text and we made a bunch of columns out of that text. And if I scroll, you'll see we got to the end of work class. Now we're at education, which was another original column. There's a whole bunch of education columns. Country was an original column. There's a whole bunch of country columns. And what it's doing is it's making a column for each possible value of that categorical variable. And it's putting a 1 where that thing was. So this person number 17,064, their work class was private. So it's putting a 1 under private, and it's putting a 0 under all the other ones. And you can only be one thing at a time. You can't be private and never worked. And that's why it's called one-hot encoding, because only one of the columns is hot. Hot meaning there's a 1 there, it's on, and it's off. It's 0 everywhere else for the work class, because you can only be one of these possibilities at the same time. So that's what one-hot encoding does. For each original column, it makes however many columns there were possible values, and then it just sticks a 1 where your actual value for that person. So this person had work class equals private. Where's my little scroll bar? There it is. And this person is from the United States, and then we're putting 0 everywhere else. So that's what one-hot encoding does. It's a transformer. It has the same syntax. Sparse equals false. We could just not worry about this for right now. It again makes things print out properly when I'm talking to you. Same with this. It's just for printing things out. You don't need to use these in general. I call fit transform, and it gives me these ones and zeros. I put it into a data frame just so we can print it out. And then again, I can smush it back with the original data frame. So I have these original 6 numeric features. And now I have, look at this, I have 108 columns total. So my, let's see, I had 8 of these categorical features, and they turned into 102 columns because I have 6 numeric features that stayed the same, these first 6, and then 102 more columns of ones and zeros that came from these 8 categorical features, because each of these 8 categorical features had multiple options. And then I can run logistic regression, and again, I don't get an error. And I'm not computing the scores right now because that's not really what this is about. We'll do that on Thursday. Yeah, okay. Yeah, I'll just say that the labels, the Y values, press the wrong button. The Y values, even if we had multiple categories, we don't need to one-hot encode the Y values because scikit-learn is okay taking those in directly as categories. But for the X values, for the features, we have to do this. So just wanted to make a note about that. I mean, target values. This we can skip, it's not urgent. And this is, yeah, this is just a giant thing that you can read over later. That was my answer to a Piazza question last year, but I'm not going to read it all out in class now. So let's go to Q&A. Okay, so there's a raised hand. Go for it.
Hi, so I was, could you scroll up to the one-hot encoder with the zeros and ones? Right.
Is that good?
Yeah. Couldn't we just treat this as a sparse matrix and create a system of equations?
What do you mean by create a system of equations? For what purpose?
Like to determine, like, see what the coefficients are, like for.
Yeah, so that's outside of the scope of the course. That's inside the scope of 340. The short answer to that question is that you can do that for a linear regression and not really for anything else. And for anything else, you need some kind of numerical optimization procedure, which is actually what's happening inside of logistic regression fit.
Okay, thank you.
There's one other raised hand. Go ahead.
Hi. Could you just elaborate a little bit more on what you meant by about how sklearn's fine with the categorical labels?
Oh yeah, sure, no problem. So I mean, if you look at our data here, sorry, I gotta go so far up to get the original data. Here, okay. If you look at the original data, so these are categories, like marital status is a category. Mm-hmm. Income is also a category, and it's strings in Python. It's not numbers. And you could have 10 income categories, and this would still work. And what I'm saying is that scikit-learn will complain if you give it X values, if you give it features that are not numbers, like if you just directly give it these occupation strings, it'll throw that error.
Oh, I see now.
But it'll let you give these target value strings. You don't have to convert these into numbers.
Oh, so it can actually read the... Oh, I see. That makes sense now. Okay.
Yeah. And that's actually what we were doing last week too. Like with the reviews, we were just having pos for positive and neg for negative, and we were just handing in those strings. We weren't like turning them into 0 and 1 or anything, and it was all fine.
All right. Thanks.
Yep. Okay, so let's see what we have here. We have some questions on Piazza. Is there no issue with preprocessing only categorical features? Yeah, so we're going to pre-process the other features on Thursday. Today we're just focusing on the categorical features, and we'll focus the other ones on Thursday. Do we ever get concerned there'll be too many columns? Yes, we'll talk about that later today. Great question. That's all we had from Piazza. I do see some chat in the Zoom. I guess people are not really going for the Piazza thing. Let's see if there's something I want to address here. This seems similar to count vectorizer. It's fairly similar, but count vectorizer is picking up the presence or absence of a word in the text. And this is just going all possible values. If you use this on text, it wouldn't make any sense because it would be like, what are all possible values of a movie review? Which is just every movie review is different. So that wouldn't make sense. Whereas here you have repeated values. You have a lot of people working in private enterprise, a lot of people working in government. So it's different in that sense. Is there any drawbacks to use one-hot encoding to encode ordinal variables? We'll talk about that later today. Are these rows the indices? Yes, so that's like the person number. If there's more than 2 target values, yeah, that's totally fine. You don't need to change it. If it was income was like low, medium, and high, you could just leave them as low, medium, and high, and everything would work. Decision tree classifier would work. Logistic regression would work. We'll talk more about that later. Okay, we have 20 minutes left. I think we're more or less okay for time here. So back to ordinal encoding, and this is exactly a question that was in a chat. Can't we just use one-hot encoding all the time and never use ordinal encoding? Well, it's a bit better to use ordinal encoding when ordinal encoding makes sense to use, and I'm going to give you an example right now. Here's our data set again. Here's the features we considered categorical features. Here's the data set just restricted to these categorical features. And the education one, I mean, this whole thing is kind of silly what I'm about to say, because it turns out the original people who made this data set already did this for us, but let's not dwell on that. The education one is different from all the other ones because it is inherently ordered. I can't really say there's an order to these occupations or these countries or whatever, but there is really an order to these education values. I mean, look at them. You could actually sort them from least to most education. And so you might want to do that. And again, this comes down to, if you had infinite amounts of training data, who cares? Do whatever you want. One-hot encode this, it'll be fine. It'll just learn separately what to do with 11. If you give it infinite amounts of data, it could basically learn this ordering by itself because there's just so much data, it'll see the evidence of what it should do. But in real machine learning problems with not infinite amounts of data, if you can give your model some of your human intuition, then it is going to do better with limited data. And so we want to give it this human intuition that these are ordered, and then we should be able to get a better score in general. And so what I'm doing is I'm putting these in order from preschool, first grade, all the way to doctorate. Just making sure I didn't miss anything. And then we can redo the ordinal encoding. And the key thing is this. I'm passing in, when I make the ordinal encoder, I'm saying this is what I want the categories to be. Follow this order instead of the default order, which was just alphabetical, which was this order, which doesn't make any sense. And now when I run the code, I'm comparing the original and the encoded. And so you can see that the higher education levels have higher numbers and the lower education levels have lower numbers. And that makes sense, because now if you have a decision tree that says if education is greater than 5, then I think they're going to high income. Well, that makes sense, because everything greater than 5 is like high education. Or if you have a logistic regression that has a positive coefficient, so that you're multiplying that positive coefficient by the education number, that makes sense. Bigger the education, the bigger you expect the chances are of having a high income. So this is better than one-hot encoding, because with one-hot encoding, you're just saying, you know what, I got 12 different education levels. I don't know anything about them. You figure out which education levels. And then it has to separately learn that doctorate is high education and master's is high education. And it takes more data to learn that because maybe you don't have that many people with a doctorate in the data set. Whereas here, you're kind of, the way you prepare the data is putting in some of your preconceived notions that are useful. I see a question in the chat that I just want to address right now, which is it okay to assume that higher education corresponds to higher income? No, we're not assuming that at all, because logistic regression gets to learn that coefficient. It could learn a positive coefficient or it could learn a negative coefficient. That's its job. And same with decision tree. It can learn whatever it wants. It could learn that 10th grade is the best possible thing and everything else is low income. So it makes no difference if this was pre-processed this way or if you took it the other way around. So if you did education levels backwards, so that now doctorate is 0 and preschool is 12, then it's fine. Everything's flipped. It makes no difference. It will just learn a negative coefficient for this feature that we've made. And it'll say, well, if this thing is bigger, the income is probably smaller. And so we're not building in the assumption in any way that higher education leads to higher income. The only assumption we're building in is that this is an ordered variable. Okay. Right, cool. Yeah, we already said all about this. So actually what I might want more is this. I might want another classification of my features to say I have numeric features, I have categorical features, and I have ordinal features. As I said, I didn't notice that the people who made the data set already turned education into an ordinal feature. And so the better thing to do would just be to delete this education that they gave us and just use the ordinal education feature that they already gave us. But in any other situation, if you had this type of feature, and we will see that when we get to the housing data set in a couple of weeks, we're going to see a bunch of features like this. We want to keep that ordering property because it will in general give us better scores and better generalization. Okay, Q&A. So let me first go to Piazza. Nothing here. And no raised hands. And a whole bunch of stuff in the chat that I'm kind of losing track of. Just give me a minute. If there are more than 2 target values, it'll be fine. Great, yeah, this is good. The outcome variable is also ordinal here. Interesting question. Okay, so in the current version of the course, I don't think I teach how to deal with the outcome being ordinal. So I should add, if you only have 2 categories like low and high, then there's not really any difference between treating it as ordinal and categorical because there's just 2. And so they're just 2 different things. It doesn't really make sense to say 2 things are ordered or not ordered. Once you have 3 things, that distinction actually makes sense. There are machine learning methods that can predict ordinal outputs, but I haven't put them in the course so far. But we're going to talk about categorical outputs where you have a bunch of different categories. But it's true that that example I gave of high, medium, and low income is not something that I really talked about unless you treated them as numbers, and we'll talk about that in a couple of weeks, but you might want to remind me about that. That's a good point. Ordinal regression is what it's called. Should we transform some categorical variables into numbers? Yes. Okay, I think we should keep going. Got 15 minutes left on the clock and an estimate of 15 minutes left of material, so let's keep going. Okay, so we haven't scored our model yet. I don't want to deal with the whole pipeline right now. We're going to do that on Thursday. So right now I'm just going to only keep the categorical variables, throwing away everything else. I'm going to make a pipeline. Before we had a count vectorizer followed by a classifier. This time we have a one-hot encoder followed by a classifier. And so fit works great. So keep in mind I'm using a pipeline here to do the encoding followed by the regression. So fit works. Training score, I get 82% training accuracy, and then cross-validation, bam, error. This should work. So what is the error here? I mean, if training score works, why is cross-validation not working? Those are basically the same thing. And the reason is something that someone posted in the chat a while ago. Let's look at the error message. Found unknown categories, Holland, Netherlands, in column 6 during transform. And so here's the different countries. So first of all, Holland, Netherlands is a country, but if we didn't know that, we could just look what column 6 was. So here's the different countries in this data set and how often they occur in the training set. A lot of US, a bit of some other things, and only one person in the entire data set whose native country was Holland, Netherlands. And so since someone posted in the chat before, I'll just keep going and say what the problem is that we're doing cross-validation with different splits. And in one of those 5 splits, this person got put in the validation set. And when this person got put in the validation set, then it's trying to call transform with the one hot encoder, but it's saying, hey, I've never seen Holland, Netherlands before. Because remember, there's only one person. So if that person's in the validation set, they're not in the train set. And so when you build the one hot encoder in the train set, it's never heard of Holland, Netherlands. And so then when you go to transform the validation, it's like, hey, what is this category that I've never seen before when you called fit on one hot encoder? Now you're telling me to transform something that I never saw during fit. And so that's this issue. So yeah, we can look at the one hot encoder. We made a column for each country, but we never made a column for Holland, Netherlands here. In this case, because in that split, in that fold, because Holland, Netherlands was not, there was only one person, they weren't in the training set there, and that's when .fit got called. So this is very analogous to count vectorizer, and someone asked this question last week too, like what if we have a word that wasn't in the training set? It's just a default behavior in scikit-learn that count vectorizer is totally cool with that. Count vectorizer has to be cool with that because sometimes you only use a small number of words. Like you say, I only want 500 words as my words that I'm making columns for, and there's gonna be tons and tons of words that are not in that list of 500 with count vectorizer, and so it's perfectly used to ignoring those. But one hot encoder, this is very different. It's not for text data, it's for categorical variables, and it says, hey, you might wanna check this out. This is weird. There's a new category I've never seen before. What do you want me to do with this? So the simplest fix to this problem is this. Handle unknown equals ignore. So that basically says if you have an unknown category, when calling transform, don't freak out, don't throw an error, just give that person 0, 0, 0, 0, 0, because they're not from the US, they're not from Mexico, they're not from China, they're from some other country, so they're just gonna have zeros everywhere. And usually with one hot encoder, you have a 1 somewhere and zeros everywhere else, but here they just have zeros everywhere, and then it will not throw an error. So if I do it that way, then it's all good. I get a score and no error. And so this is a useful thing and a not unreasonable thing to do in a decent number of scenarios. But yeah, I want to just think critically for a minute about, is this a good thing? When do I want this? Do I want to not be told about this, right? Just ignore this issue, or do I want to be told about this? And so it kind of depends. Having the all zeros everywhere is kind of like an other category. So if you were in deployment, if someone was from Holland or Mars or Hogwarts or whatever, those would all be treated the same. Anything that's not been seen before, it's just becoming 0, 0, 0, 0, 0. And so if you're okay with all possible unseen categories being treated the same, then this is fine. Again, this gets very nuanced. So you would do your cross-validation, you would do your hyperparameter search, whatever, but typically at the end, you would retrain on your whole training set, at which time you will have seen Holland. But then maybe when you go to your test set, there's another country in the test set that you haven't seen before, and so then you got another error. So you have to be a bit careful about this. Sometimes you say, you know what, this is all a waste of time. I know what all possible categories are in advance. For example, if the feature is provinces or territories of Canada, we just know what they are. We can write them down, BC, Alberta, etc. We can make a list of those 13 things, and we can just say, you know what, here they are, make 13 columns. I don't want to hear about this error anymore. And then you don't need to tell it to ignore, because that error is just never going to happen. You know it has to be one of these 13 things. You write them down, you make columns for all of them, and then you're good to go. And so you could kind of say it's a violation of the golden rule. So what I'm doing here is I'm taking the original data set even before the train test split, which I basically say don't do. There could be certain situations where you're like, you know what, I'm just going to take all these, make categories for them. And it's not like the biggest crime ever, but it's something to think about. You basically want to think about, when I get to deployment, what if there's a new category there that's not in any of my train or test data? How do I want that to be handled? Maybe you do want it to throw an error, or maybe you do want to ignore it. You have to think about that in kind of a domain-specific way. But what I want to show here is you can pass as an argument to one hot encoder, categories equals all countries. And now you're just telling it, hey, these are the columns I want. You don't need to look at what's in there. And it's the same with count vectorizer, actually. You can pass count vectorizer a list of words, and then it will not even look at what words there are in the data set, because you're just telling it, you know what, these are my words. So same here. You can just say, hey, these are my categories. Done. This is what I want. Okay. Yeah, so as far as the golden rule is concerned, well, I guess I talked about this a little bit. But yeah, if you're presetting the categories, then there's not this golden rule issue of like the different rows looking at each other when they get pre-processed, because you're just predefining how to pre-process each row. Kind of a minor point. Okay, I'm just going to keep going full speed ahead in the interest of time. So there's another popular argument in one hot encoder. This one. So here's my original thing with default values. I get all this. So I'm just looking at the relationship feature here. So I have husband, non-family, all these kinds of things. And then there's this thing called drop equals first, which is fairly common thing to do in one hot encoder. And what it does is, remember the first one, you had husband, then not, and family. It drops the first one. So that's why it's called drop equals first, is because it throws away the first column. And you might be saying, well, that's ridiculous. Why would you throw away a column? But the reason why it's not ridiculous is that if you see 0, 0, 0, 0 here, you know there must have been a 1 for husband. You know this person must have been a husband because it's one hot encoding and it's 0, 0, 0. So there must have been a 1 that got thrown away. So you can actually take this transform thing and get back to the original, what category was it? And so in a sense, you're not losing information. All the information is still contained in this ones and zeros. And in a way, having that husband column was kind of redundant, because even when you throw it away, you can already look at this and know what category they're in. And there's some theoretical reasons why this is appealing, to not have that redundancy. And yeah, that's why it's popular. Oh, I'm just saying here, if you look at this 0, 0, 0, yeah, you can see that it was actually husband. Okay, already talked about that. So I don't want to go into this too much, but I just want to say I don't like this for a number of reasons. But I just want to say that in bold, because I see a lot of this. And part of what I'm trying to do with this course is tell you, just as a baseline, here's some rules of thumb you can follow, and then you can deviate, you know, as needed. But I don't like this. So I wouldn't use it unless you really thought about it and have a reason to use it. So the reason why it's popular is it has some appealing theoretical properties. As I said, there's this redundancy. And in a certain case, in particular with linear regression, so if we have some statisticians in the room, then you're used to doing this. And in fact, you have to do this in certain cases, like with linear regression. But the good news is I'm going to tell you to never use drop first, and I'm going to tell you to never use linear regression either. And so you'll be in the clear. And we'll get into this more in 2 weeks when we talk about regression. And I'm going to recommend an alternative, which is the ridge regression and other things like that, which will solve this problem. So long story short, there are some reasons to do this, but I'm just trying to set things up so those reasons don't apply to us. And there's a lot of reasons not to do this, which is why I really don't like it. It prevents you from doing handle unknown equals ignore, which is a really useful option that we just talked about. because both of those try to use 0, 0, 0, 0 to mean something. And so they just get in conflict with each other and scikit-learn complains. It makes feature importances more confusing. We'll talk about that in a few weeks. It makes feature selection more confusing. We'll talk about it in a few weeks. So long story short, not recommended by me. Okay, and I'm just going to keep going here. Sorry, I would love to take questions, but I want to finish the material. We only have a few minutes left. So the next thing is categorical features with many categories. And that's also something that someone posted about in the chat a few minutes ago. So yeah, here's an example with many categories, country. So do we really want 50 columns for the country? And doing so can actually result in overfitting. It can result in all kinds of weird ways. And you know what? Do we really have enough data to learn, say, with Cambodia, we only have 13 people. Is that enough to actually learn about whether how Cambodia affects the income prediction, or is it just going to be overfitting because that's not enough data? And I would argue, you know, that you might just be overfitting. Whatever you decide about Cambodia, should it be a positive coefficient, a negative coefficient? What should it be? Remember that logistic regression gives you a coefficient for each column, and one-hot encoding turns each of these options into a column, and thus logistic regression is going to end up giving you a coefficient for each category in these categorical variables. So Cambodia will have a coefficient, Honduras will have a coefficient. And is this really enough data to learn that coefficient? You know what? Not necessarily. Maybe I don't need 50 columns here for this country thing. And so there's a few solutions. One is you can just group them together. You can have an Asia bin, a Europe bin, and then you'll have a bunch of data in each bin. And that's a reasonable approach. And maybe you'll try some of these different approaches, and we'll actually explore that later in the course. But another thing you can do is just have an other category to catch these cases where you don't have a lot of data. So here, these are the most common 5 answers in the data set. And so what I can do is I can make a one-hot encoder where I specify the categories to be the most common, to be these 5. And then I can set this to ignore. And so now if it's anything other than these 5, it'll not be on the list of categories. And so it'll just be like a 0, 0, 0, 0, 0, which is kind of like the other scenario. So that's something that I think is pretty reasonable thing to do. So now all these people are from the US here, but this person is not from one of those 5 countries. And so any other country is just going to be 0, 0, 0, 0. And now you only have 5 columns instead of 50 columns. And there are pros and cons to doing this, but you may try this and you may see that it's better this way and you just don't want all those columns, and this actually gets better results. Okay, in the last minute, I'll just say that there's one other parameter I want to know about. Unfortunately, the only binary feature in this data set is sex, so I'm going to use that. So there's male and female in this data set. And in this case, it seems particularly unnecessary to one-hot encode this as 2 columns. And so that drop first thing I was talking about earlier would drop this first one and just keep only the other one. And when you really have only 2, it does seem kind of excessive to have both of these columns and kind of unnecessary because the 1 and the 0 can just represent the 2 columns. And so there's also a drop equals if binary that I do recommend that basically says it's like drop first, but only do that if the feature only has 2 values. And so we can see that happening here, and it just arbitrarily picks one of them. In this case, female was first because of alphabetical order, and it dropped the first one. I know I went way too fast in that, but I really always like to end on time, so I'm going to end here. And please follow up on Piazza with questions because I know I went really fast at the end there. That's all for today, and see you Thursday.